Welcome. In this video, we will take a look at three different algebraic limit techniques. So let's dive into the first problem, A. In our first problem, we have a function x squared minus 6x plus 4. We want to take the limit as x goes to 2 for that function. We'll notice that this function is actually continuous over its whole domain. It's a parabola function. And so in this case, the limit value at 2 is going to be the same as the functional value at 2, since it again is continuous. So this is a continuous function. So here we can just evaluate this limit at x equals 2. So this would be 2 squared minus 6 times 2, and then plus 4. If we work this out, we'll have 4 minus 12 plus 4, which will give us a minus 4 to be the solution. So as x approaches 2 of our function, that will go to negative 4. There we go. Again, we can evaluate this limit at x equals 2 because the function is continuous. That will change here in part B. Part B, we're going to have to use a little bit more of a refined technique. Here we want to take the limit as x goes to 4 of this rational function. So we have a second degree polynomial in the numerator and a second degree polynomial in the denominator. And you'll see that if we just evaluate this at 4, the denominator here will actually be equal to 0. That'll be 16 minus 24 plus 8. That'll be 0. And we can't divide by 0, so we have a problem there with that rational denominator. So one technique here that we can use is to think about if we can factor kind of that problem out. And so let's take a look at factoring both the numerator and denominator if we can. The numerator looks like it's a perfect square. So difference of squares here would be x minus 4 and then x plus 4 for that difference of squares. And then we have a factoring of the quadratic in the denominator. We can say that would be x minus 4 again, and x minus 2. So we can see that there is some common factors in the numerator and denominator. This x minus 4 here can actually cancel. And so when we consider the new limit, what we know to be true is that the new limit, and we'll write this down below, the limit as x goes to 4 of x plus 4 over x minus 2, this is equivalent to the original limit that we had in the problem. Those two limits will actually give us the same result, where x equals 4 was that removable discontinuity. In other words, that represented a hole in our graph on the original function. And so let's take a look at the final limit here, the limit as x goes to 4 of x plus 4, x minus 2. We can just evaluate this now that we are continuous at x equals 4. We can say that this limit is going to be 4 plus 4 over 4 minus 2. And if we work that out, that would be 8 divided by 2, or we can call that positive 4. So that final limit will be equal to positive 4 in that final form. Let's take a look at a third technique in Part C. Part C is looking at a one-sided limit. So here we are saying we want to take the limit as x goes to 1 from the positive end, that would be from the right. And we'll notice that if we just evaluate again at x equals 1, we're going to have an undefined function. So we are not continuous at x equals 1. So one thing we want to consider with this one-sided limit is what kind of values are we actually evaluating this limit at? We want to consider here values of x that are slightly larger than 1 and see what happens to the function. So the values we want to consider are maybe something like 1.1, 1.01, 1.001, getting closer and closer to positive 1, but from the right or from the positive end. So let's just consider what is happening to our function for both the numerator and denominator when I evaluate at values such as these. So in the numerator, we're just going to get some positive value. It'll be somewhere close to, looks like 4. So it'll be kind of a positive 4 value. And the value here is not important, but the kind of important piece is it's going to be positive in our numerator. And then in the denominator, let's consider what we'll have. We'll have a really small value, but it will be a very small positive value. If I evaluate at, say, 1.1, 1.01, or 1.001. So it's getting to be very, very small, but it is a positive value. So this is going to be some small positive value. So let's just consider that ratio. We have a positive number, very large in relation. 4 is going to be large in relation to this denominator, and they're both going to be positive. So when I consider what this ratio now is going to converge to, I have a large number in the denominator, a very small value, or value that gets smaller in my denominator. And so this limit here, that ratio, is actually going to tend towards infinity. As my denominator gets smaller and smaller, the fraction as a whole is going to shoot up to infinity, and in this case, it's going to shoot up to positive infinity. So this would be here our solution to that limit problem as x approaches 1 from the right side. So these are 3 different techniques for limits. One when our function is continuous, that was our part A. One when we need to maybe factor a rational function to pull out the hole that's in the graph and then evaluate. And then considering one-sided limits. So part C took a look at one example where we have to consider a one-sided limit where we are undefined at that limit value. So I hope this helps with a few techniques with algebraic limits. In our next video, we'll take a look at limits at infinity.